I want to start by examining the idea of shells and subshells. And before we do that, I just want to point out some of the misconceptions that people have about what shells are. And I think they partly arise because of the diagrams we often see drawn in books, which show atoms as having a nucleus in the center, and they'll show electrons in shells, which would be drawn as circles around the nucleus, like this. And most people, when they're asked to draw an atom, this is what they will draw. They will say, well, the first shell is represented by this circle, which contains 2 electrons. The second shell, which is represented by this other circle, contains 8 electrons. Now, this often suggests to the reader that electrons are moving in orbits, and some people think that these are exactly the same thing as shells. And this is what I want to clarify, that this is actually not the case at all. Electrons are moving definitely around the nucleus, but the movement is not in neat circles. So for example, if I was to draw a nucleus, the electron is something that would not be moving like this, but would be moving more like this. You wouldn't be able to find a very neat path that it follows. However, in its movement, if you were to track its movement, you would see that it's restricted to a particular region of space. So if I was to sort of take a snapshot of this electron repeatedly, and the first time I take its photograph, I find it's here, and the next time I take its photograph, it's here, next time it's here, next time here, and I keep repeating this process. What I will find is that I will create, and I superimpose all these plots, I will create this plot which will show that this electron is restricted to a particular region around the nucleus, and this region may have a particular shape. So for example, I may find that it's restricting its movement mostly to a spherical region around the nucleus. This region then, which is a sphere, I would call the orbital. An orbital is defined as the region of space in which the electron is most likely to be found. So you may occasionally find the electron moving away from this region, but that will be for just a very tiny fraction of the time. Most of the time, like 99% of the time, you'll find it in a particular region, which you can represent by a particular shape. And this is very, very different from the idea of an orbit. So that's the first thing that needs to be clarified. Secondly, this electron that will be in this orbital will have a particular energy level. And energy level is basically what we call the shell. Shells represent energy levels, and subshells also represent energy levels. So if shell is an energy level, then subshell is a sub-energy level. So the first thing is we should not confuse these two concepts. They're not the same. An orbital is like physical space in which the electron is, and shell is referring to the energy level. Now it just so happens that every electron in every orbital will also correspond to a particular energy level. So we can say that this particular orbital belongs to a particular energy level. So this spherical orbital might belong to the first energy level or the first shell. So what you'll see written in books is that shells contain orbitals. What that really means is that the electrons in those regions of spaces have a particular energy level, or they share a particular energy level. So I want to go back to just some ideas about what shells are to begin with. The first thing to note is that energy levels that exist in an atom, they don't exist on a continuum. They are discrete levels, and which is what we call quantized energy levels. The idea comes from the name for packets of energy, which are called quanta. So we can either have a packet of energy, or we can't have a packet of energy. We can't have half the packet of energy. So that is something that this idea is based on. So you will find that electrons are either at one level or at another level, and this is where we came up with the idea of principal quantum shells, which you already know, as represented by the symbol N. They are 1, 2, 3, 4, and so on. The first quantum shell containing a maximum of 2 electrons, second maximum of 8, and so on. Now, subshells is also, like the word suggests, is talking about energy levels. So it's not enough to just talk about the quantum shells. We also have to talk about subshells, and that will become clearer when we talk about ionization energy trends and other properties, why subshells are important. But for now, let's just introduce ourselves to the concept of subshells. Subshells are some energy levels, and like I said, the orbital, any orbital that you look at will belong to a particular subshell, and the orbital is a region of space where there is a high chance of finding a particular electron. And we clarified that orbit and orbital, those are two very different terms with very different meanings, and we should take care to not confuse the two. Each orbital, which is the region of space in which we find an electron, can contain up to 2 electrons only. The reason for that is that if you have more electrons stuffed into the same space, electrons are negatively charged, so they will repel each other, and that's going to cause a lot of repulsion, and that wouldn't be a feasible arrangement for the atom. So it can't sustain more than, each orbital can't sustain more than 2 electrons. Now let's look at some energy levels diagrammatically. The numbers you see on the screen, 1, 2, 3, these are the quantum energy levels, and these are what you're already familiar with. So 1 contains a maximum of 2 electrons, second quantum shell contains maximum 8, and so on. So these are now further split into sub-energy levels or subshells. So what we're showing here is each box is representing an orbital or a region of space where electrons are found, and these boxes are distributed in this diagram based on the energy level that they possess. So the first one has the lowest energy level, so that is the first subshell. This orbital belongs to the first subshell, and this is the 1s subshell. Then we have the 2s subshell, which also contains just 1 orbital. The 2p subshell contains 3 orbitals, or 3 regions of spaces where electrons can be found, and each one can contain a maximum of 2 electrons, so which is why this 2p subshell can contain a maximum of 6 electrons. And if we look at the entire quantum shell, there are 4 orbitals, which means they can contain, this entire quantum shell can contain 8 electrons. Then we move on to the third quantum shell, which is split into 3 subshells or sub-energy levels, the 3s, 3p, and 3d. Overall, you see that it has 10 plus 3 plus 1, so that is, 5 plus 3 plus 1, that is 9 orbitals, and it can hold up to 18 electrons. Now notice something interesting here. After the 3p subshell, the next energy level is 4s, and then we have 3D. So here things get a little complicated, and we'll come back to this later on as well, as this has important implications that we need to consider later on in the course. But for now, let's talk about these regions of spaces and what they look like in each subshell. So first up, we have our 1s subshell, which only contains one orbital, and this is spherical in shape. So how do we know that? Well, if you were to sort of take snapshots like I was trying to show you earlier on and superimpose them, you'll find that each time you look at the electron, most of the time it's found in the spherical region around the nucleus. The 1 represents the quantum shell. S represents the subshell, which is the sub-energy level. It's the 1s level is the closest to the nucleus. There's only one orbital here, and this orbital is spherical in shape. And the other quantum shells will also contain an S subshell. The S subshell, wherever you encounter it, is going to be spherical in shape. So 2s will be very similar to 1s. The only difference would be that 2s is slightly bigger in size. The reason is that the electron now has more energy, and if it has more energy, then it's able to exist further away from the nucleus. It's able to resist the attractive pull of the nucleus a bit more than the electron in 1s. So you will find that it will occupy a region of space that may be a little further away. Similarly, 3s and 4s, each quantum shell has one type of subshell, S, which is a mandatory type, and that is always spherical, and it only contains one orbital. The shapes would get just bigger and bigger, so you can diagrammatically just show them as larger circles on paper representing spheres. Then we come to the P subshell. Now we found that this was something that contained 3 orbitals, and those 3 orbitals were at the same energy level. Now these orbitals are not spherical in shape. They are in fact dumbbell shaped, and what that looks like is something as shown in the diagram here. So you have, if you were to do the same plotting as we did with the S subshell, if we were to actually take electrons and take snapshots and sort of superimpose them, this is the kind of plot that you would get. It would exist in a dumbbell shaped region around the nucleus. Now this is just one of the orbitals in this subshell. Now this subshell has 3 such orbitals, and each one is dumbbell shaped. Now this is, so suppose if you were to zoom in on the second quantum shell, this is the second quantum shell. It consists of 2 subshells, which are the S and P subshells. The P subshell further contains 3 orbitals. Now we have 3 dumbbells basically here, and this one is spherical in shape. Now how do these 3 dumbbells exist around the nucleus? How is it that we are getting this shape, and how would they all, what would the atom look like if all of them were represented together? Now this is something that you would be able to understand better through a video that I have for you. I just want to show that. If we were to imagine 3 axes, x, y, and z in space, which are represented by the arrows here in this video, then this is what the orbitals would look like if the atom had 2 quantum shells filled. So the first one, 1s, would actually be spherical in shape, and this is something that's going to look like this. 2s would also be spherical in shape, but this would be bigger, and we said this was because the electrons have more energy. 2p would contain 3 orbitals. The first one, if I place on the red axis, which I can call the x-axis. Then the next one I place perpendicular to it in order to minimize repulsion. And the third one I will also place perpendicular to the other two, which is why I can give them the names Px, Py, and Pz, indicating that they're all perpendicular to each other. Now this is what an atom really looks like. Oh, this is closer to the actual depiction of an atom if it had two quantum shells filled. And as you can see, this is very different from the diagram that you've seen in books that we were discussing earlier.